All right, welcome back. This is 11.6, video number 3, and we're going to solve this three-dimensional system of equations using Gaussian elimination. All right, so our first step, just like with the two-dimensional system, is to put this in an augmented matrix. Let's go ahead and do that. So we have 1, 2, 3, minus 1, 3, minus 2, 1, minus 1, minus 9, 8, minus 2, 9. And let's check all those because it's really easy to make a mistake. 1, 2, 3, minus 1, 3, minus 2, 1, minus 1, minus 9, 8, minus 2. Okay, I feel good about that. All right, well, we need to get this into row echelon form. The way we're going to do that is we're going to start at the top and work our way down. This first value is already a 1, so we don't really need to worry about that one. That one's already 1. We don't need to scale it, but we do need to get rid of this 2. The way we're going to get rid of the 2 is we're going to take negative 2 times row 1, and we're going to add that to row 2 and replace row 2 with that result. So row 1 and row 3 are staying the same. What I like to do is I just get a different color and I take negative 2 times row 1, I just write it above. So that would be negative 2. Negative 2 times negative 1 is positive 2. Negative 2 times 1, negative 2. Negative 2 times 8 is negative 16. And now I'm taking negative 2 and 2 and I get 0. 2 and 3, I get 5. Negative 2 and negative 1, I get negative 3. Negative 16 and negative 2 gives me negative 18. All right, I got 1, 0. Now let's go for the next one. The next number I'm going to go after is this 3 right here. To get that, I'm going to take negative 3 times row 1 plus row 3 and replace row 3 with it. Again, let's transfer down the rows we're not messing with, which is row 1 and row 2. Right. So this time we're doing negative 3 times row 1. Negative 1, 3 times 1 is negative 3. Negative 3 times negative 1 is 3. Negative 3 times 1 is negative 3. Negative 3 times 8 is negative 24. All right, we're adding negative 3 to 3 and getting 0. 3 to negative 2 gives me 1. Negative 3, negative 9 gives me negative 12. Negative 24, positive 9 gives me negative 15. Pretty sure that's right. All right, we're in good shape now. What do we do now? Well, I can see as I look at the first column, it's already done. Now I look at the second column. What I would really like is I'd like the 5 here to be a 1, and I can see that row 3 has a 1, so I'm just going to switch these two rows. So we're going to swap row 2 and row 3. Right? So row 1 is the same. Row 3 is now row 2. And again, when you're doing these row operations to get your matrix into row echelon form, you want to start at the top and work down. All right, now what do I need to get rid of? I need to get rid of this 5 right here, right? So what I'm going to do to get rid of that is I'm going to take minus 5 times row 2. I'm going to add it to row 3, and I'm going to replace row 3 with that. So that's going to be 0 times negative 5 is 0. 1 times negative 5 is negative 5. Negative 5 times negative 12 is positive 60. Negative 5 times negative 15 is positive 75. All right, let's try this. Oh no, where am I? I bumped up somewhere. Here we go. All right, so let's give this a try. So row 1 is staying the same. Row 2 is staying the same. Row 3, that's what we're working with. Negative 5 Oh, well, we should do this one. 0 and 0 makes 0. Negative 5 and 5 makes 0. 60 and negative 3 makes 57. 60 and negative 3 makes 57. 75 and negative 18, I hope that also makes 57. Minus 20 will be 55 plus 2, yep, 57. Whew, that's good. All right, this is looking pretty good. Now the only thing we need to do left is we need to get this 57 out of here and make it into a 1. So what I'm going to do is I'm going to take 1/57 or divide by 57 times row 3 and replace row 3 with that. And I'm going to do that up here. Let's zoom out just a little bit because I'm running out of space here. So row 1 is the same. 1 minus 1, 1, 8. Row 2 is the same. 0, 1, minus 12, minus 15. Row 3 is now 0, 0. Divide 57 by 7, you get 1. Divide 57 by 57, you get 1. And now we have our matrix in REF, row echelon form. I'm actually not going to stop here because I'm going to take this one step farther and get this into reduced row echelon form. And that's the form where you have 1s on the diagonals but 0s everywhere else in the coefficient part of the matrix. So let's go ahead. We're really rolling with our row operations. Let's go ahead and put this into reduced row echelon form. I have a plan for this. All right, so what I need to do this is when you go from row echelon form to reduced row echelon form, you go sort of the opposite of getting it originally. You start at the bottom and work up. So the first thing I'm going to try and get rid of is this negative 12. And I'm going to do that by multiplying 12 by row 3 and adding it to row 2 and replacing row 2 with that amount. All right, so 12 times row 3 would be 0 times 12 is 0. 0 times 12 is 0. 1 times 12 is 12. 1 times 12 is 12. So my new matrix would be, again, row 1 is staying the same. Row 3 is staying the same. And row 2 is going to be 0 plus 0 is 0. 0 plus 1 is 1. 12 plus negative 12 is 0. 12 plus negative 15 is negative 3. All right, we are almost there. We just have a couple more things to get rid of. We need to get rid of this negative 1 right here next. And the way we can do that is just by adding row 2 to row 1 and replacing row 1. Row 2 plus row 1 replaces row 1. No scalars this time. So row 3 stays the same. Row 2 stays the same. Those guys are where we want them to be in reduced row echelon form. So we're just working on row 1. 0 plus 1 is 1. 1 plus negative 1 is 0. 0 plus 1 is 1. Negative 3 plus 8 is positive 5. We are really close. One more step. We just need to get rid of this one right here. And so what we're going to do is we're going to do negative 1 times row 3 plus row 1 replaces row 1. 0, 0, 1, 1. We're not mucking with row 3. We're not messing with row 2. Minus 1 times row 3 would be 0, 0, minus 1, minus 1. 0 plus 1 is 1. 0 plus 0 is 0. Minus 1 plus 1 is 0. Minus 1 plus 5 is 4. So we are finally done, and we are in reduced row echelon form. That was a lot of arithmetic. However, now, when we translate this back to a system of equations, we don't have to do any work at all. Look at this bottom value. This says 1z equals 1. Right? This row says 0x plus 1y plus 0z equals negative 3. So it tells me y equals negative 3. This tells me 1x plus 0y plus 0z equals 4. And there's my answer. X equals 4, y equals negative 3, and z equals 1. And now you're saying to me, or to yourself, this is a lot of work. And it is indeed a lot of work. And you're going to say to me, maybe, isn't there an easier way to do this? And I'm going to say, yes, there is an easier way to do this. It is important to understand what computers are doing, but it's also important to let computers help us. So let's go over to Desmos and practice solving this using Desmos. All right, here we are in the Desmos matrix calculator, and we're going to use this to help us solve the problem we just did. You do have to know how to put a system of equations into a coefficient augmented matrix. So let's go ahead and do that. We'll call the matrix, whatever comes up, A, and this matrix was 3 rows and 4 columns. And let's go ahead and fill in the values from our augmented matrix, the original one. So it was 1, -1, 1, 8, 2, 3, -1, 2, 3, -2, -9, 9. All right, so there's our matrix A. And now to get this into reduced row echelon form, you type RREF, and you apply that, oops, that's not an F, RREF, and you apply that to matrix A. Oh, well, something has gone terribly wrong. What did we do wrong? Did we type in the matrix wrong? Yep, we did. What do they want this to be? A -2. There we go. See, it's nice you can actually go back up and fix it if you see a mistake. So I didn't copy my matrix over accurately, which happens. And now we can see our answers. And this is exactly the matrix we got from our reduced row echelon form. And this tells us that x is 4, y is -3, and z is 1. All right, let's do example 5. This time we're just going to put it into a coefficient matrix here, and then we're going to go use Desmos matrix calculator to get it into row echelon form. So let's put it into our coefficient matrix. 1, 5, 2 for the x coefficients. 1, -3, 6 for the y coefficients. -4, -2, 7 for the z coefficients. And -4, 0, 30 for the right-hand side. All right, let's go over to the matrix calculator and see what we get. All right, let's go ahead and put our new matrix in here. This time we have a 3 by 4, and let's put in our values. 1, 1, -4, -4, 5, -3, -2, 0, 2, 6, 7, 30. And put it into reduced row echelon form. And we got all 2's for our solution. All right, looking at example 6, let's go ahead and put this into a matrix. It's going to be 3x plus 4y equals 12, 6x plus 8y equals 24. All right, let's go over to Desmos now and let Desmos help us solve this by putting it into reduced row echelon form. So we're going to get a new matrix, A, but it is 2 rows and 3 columns. And it's 3, 4, 12, 6, 8, 24. Enter. And now we're going to reduced row echelon form this guy. And what do we get? We get kind of an unusual answer. We get 0 plus 0 equals 0. And we get x plus 1 and a third y equals 4. So what does this mean? It means we have a dependent system of equations. Whenever you see a row of all zeros like this is a true statement. 0x plus 0y equals 0. That's not saying like 15 equals 0. This is saying it's a dependent system. And actually, if we go back and look at the equations, if you see that the second equation is exactly 2 times the first equation. 3 times 2 is 6, 4 times 2 is 8, 12 times 2 is 24. All right, out of Desmos, we got this solution that showed us it was a dependent system, but let's write it down and look at it a little more carefully. 1.333 we know is 4/3. And actually, we could even put the fraction button if we wanted to, and it would have told us 4/3. I should have done that on Desmos. Do it now on your own. All right, so how do we write this solution of equations? Do you remember back from section 11.1 when we had dependent systems in 2 dimensions? This second equation row of the matrix doesn't tell us anything, but the first one tells us that x plus 4/3 y is equal to 4. And the way we did this was we solved for y equals, so we're going to subtract x from each side. 4/3 y equals minus x plus 4. Solve it for y, multiply each side by 3/4. That gives me y equals minus 3/4 x plus 4. And remember how we wrote this? We wrote a c for our x value, any constant, and then minus 3/4 times that constant plus 4 for our y value. So that's how we wrote the answer to a dependent system of equations. And remember, if we wanted to find 1 point on it, we could pick c to be anything we want. For example, if we pick c to be 4, then x would be 4, and y would be minus 3/4 times 4 plus 4, which is minus 3 plus 4, which is 1. So 4, 1 would be one solution of this equation. There are infinitely many, and they're all of this form.